Thank you for coming out tonight. How many people here are not from Harvard? Yay, look at that. Thank you for coming and welcome. This is our research lecture series, and this is the third one this fall, and the last one of the fall. We couldn't find anybody who wanted to give it in December for some reason. But then there's a whole slew of talks in the spring, so I hope you'll come back for that, and we'll send you email if you left your email at the desk there. Okay, so tonight we're going to have another physics talk, but it's sort of chemistry, so this is going to count for chemistry, right? Yeah.
You can ask the chemistry department whether they can count it.
So I have my new colleague. I'm very excited to introduce my new colleague, Philip Kim. I tried to find out Philip Kim's, he was born in Korea and grew up in Korea, went to Seoul National University. A nice hat. Thank you. You're welcome. And I tried to find out his Korean name, but it turns out it's Philip Kim. But it's not pronounced that way. So he erased it, unfortunately. But anyhow. But I think it's Philip Kim. So apparently I learned something great today. Anyhow, after Seoul National University, he came here to Harvard in applied physics and did his PhD with Charlie Lieber. And then he went away to Berkeley and on a Miller Fellowship and stayed there a while in California. But he wanted to come back, so he came back to Columbia University where he was assistant professor, associate professor, big shot professor. Then something was missing in his life. He couldn't figure out what it was. Turned out it was Harvard. So he came back to Harvard just this year. So we're very lucky to have a talk from him. Philip, he's pretty famous. And he's got a lot of prizes, like the Oliver Buckley Condensed Matter Prize and the Hoam Prize. But I want to tell you a little story. Don't tell anybody. There's a couple of guys who got the Nobel Prize. And when they were getting the Nobel Prize, they have to give a speech. And in the speech, one of them, Andre Geim, hope I pronounced that right, is quoted as saying this. I owe, he said it this way, I owe Philip a great deal for this, and many people heard me saying, before and after the Nobel Prize, that I would be honored to share it with him. And so what we have tonight giving us a fantastic public lecture is a guy who got the Nobel Prize without the money. And that's even better. So I want you to welcome Philip Kim.
Thank you. Thank you. Yeah, Melissa told me that she prepared something embarrassing. I didn't know actually this was it. Oh, thank you. Yeah. Oh, thank you very much for coming. I know this is getting late and then darker soon, so it's probably not feels like much kind of late in the night. But so I'm going to tell you today about some part of my research, but more generally that tied with that kind of big word in the physics. And as you see the title, that the relativities, quantum mechanics, and then something like the graphene that I'm going to explain. This is a relatively big topic, and I chose that because it's kind of fun that we can go back to some things interesting, basic physics, but important physics that may connect to many things. High energy, low energy physics, even chemistry, right? So that's basically my ambitious goal, and I'm not sure whether I will kind of fulfill that goal today. But nevertheless, let me start with this really famous photographs, and everybody have seen in their life at some point, especially if you're interested in physics. This is probably the most famous physics conference picture. Part of the reason is about 30 people in this picture. 17 of them got the Nobel Prize already back then, or would get it after this conference and so on, right? These are the kind of really great mind of the modern physics, I would say, and really exciting time. 1927, that was taken at the Leonid Park in Brussels. And we may ask, why actually gather there? Well, the conference title comes like this. This is the 5th Solvay International Conference on the electron and photons. back then, those electrons and photons, we know that existence of them, and that was those are the kind of one of the fundamental particles, probably the two fundamental particles known well back then, right? And they want to know that how one can describe the physics of those kind of fundamental particles. And already there, the relativity is already started established as kind of well-known, kind of one of the important modern physics pillar. And the quantum mechanics is about to born, or already born at that time, just born, right? So that's basically exciting period of the physics, I would say, modern physics, that everybody wants to know that how to describe this kind of new world using the new languages. Now, to understand those kind of important part of the two pillar, I think I want to kind of wind back a little bit because that story is that related, deeply related to the what I'm going to tell you today. So let me just wind back a little bit, kind of slightly back, about 80 years back, and just think about the beginning of the modern physics, or beginning of this completion of the classical physics. In 1965, James Clerk Maxwell actually discovered a really important part by just kind of establishing so-called Maxwell's four equations. He discovered, in fact, light is propagating electromagnetic waves. And that is an important statement because we know that, well, we know the electricity and magnetism, or we know about the optics, but that somehow that's actually combined into the one gigantic big field, an important field. And saying that light is the, in fact, traveling electromagnetic wave means that we know about the wave, and water wave actually propagating the medium, which is water surface, sound wave propagating in the air, and they all kind of propagate at a certain speed. So one should be able to know that what is the speed of the light as a propagating wave, right? So after Maxwell's this claim that, that there are many other experiments, but among the one of the important experiments that has been carried out is how we can measure speed of the light and whether the speed of light actually can changes. Well, if you think about the wave is propagating in the medium, of course, if the medium starts to move relative to you, you expect actual speed may get changed. So this is important questions. And the answer actually comes from the experiments, and by the important experiment and ingenious experiment, I would say, carried out by two American physicists, Michelson and Morley, devised actually this Michelson-Morley interferometer, sitting into the basement of the Western Reserve in Cleveland, Ohio. They need kind of really, really stable instruments back then to measure this little change of the light speed, if there is any, right? And this gigantic interferometer was floating on the top of the bath of the mercury. Out of 2 years experiments they actually carried out, especially try to measure the speed of the light changes, potentially due to the medium speed changes, what you call the ether speed, wind. Actually, they come up to conclusions, which is kind of boring or maybe even disappointing. They actually they couldn't find any change of the speed of the light over 2 years of time period, potentially changing this medium speed. But this is relatively intriguing, but it turns out a very important conclusions. If we really do believe that the conclusion that they made out of experiments, it's kind of quite intriguing case, right? Because in some sense that if we change the medium speed relative to that your observations, you surely see that speed of this wave propagation should change. Here I just brought the kind of my first demo. This is a torsional oscillators that can create a wave that propagating through the string. If I just make that, you can see that wave is propagating that. And with speed about a meter per sec type of the speed, right? So imagine that this is a light propagating the medium, ether or vacuum or whatever. Then you can say that, ask that, hey, so if I just move the relative to this medium, or let me just kind of move medium for relative to you, and ask that whether the speed got changes. So let me see whether I can do this, right? Of course, if my medium is moving faster, you can see the wave is propagating faster here. Now, in the other way, let's see that. Let me settle this one and change the medium. And if I just move backward, it doesn't work, but you get the sense, right? Speed of wave propagation surely changes how this cart moves, right? Apparent speed. But this experimental result claim that that's not the case for the light. Now here comes a really another ingenious theoretical predictions or presumptions. Based on this experimental result, Albert Einstein actually take this really seriously. and consider, all right, so we will not change the speed of the light, whatever frame you take, whatever speed you just medium moves, right? But then doesn't make sense because it's our intuition tells us that, well, if the medium moves a relative speed, I should see that different speed. What should I change to keep this statement? And there comes from really kind of important kind of several conclusions. The first important conclusion is, well, then you have to change your concept of the time and the length scale. In other words, if you just move in the different scale, the only way that you can do that is you have to change the time in the moving scale and also the length scale. And if you start to change the time and the length scale, then all of your dynamics got changes. Your force got changes, your momentum got changes. And after that, you got in the weird world. Somehow the mass is that related with the energy of the system, then this object can shrink then when you start to move. If you have the measuring the time on the moving clocks and the clock actually start to run slow and all this sort of, probably you heard about all this relativistic, the changes start to appear starting from this simple statement. We don't need to go through all the details, but I want to kind of make the one important things that are need. This is kind of few equations I'm going to use in the class, in this lecture, and simple enough that we can probably catch. So imagine that I have the classical this system. Then if I just kind of connect the momentum of an object with energy, it's well known from Newton's mechanics. Basically, energy is proportional to the square of the momentum. It's related, basically, if you just drop the ball start kind of speed up in the constant velocities. Changing of the constant potential energy will just kind of increase the velocity square. So that's related with exactly this relation. It's a well-known relation. But once you just kind of accept all these relativistic dynamics, then you get different conclusions than how that you can connect energy and momentum. Energy and momentums are not connected with the square relations, but more complicated relation. It contains in some sense E equal mc squared because even if you have the zero momentum, you actually has energies proportional to the mass of this object, right? But what if you just get into really deep into the relativistic limits? You just kind of accelerate these particles up to the very close to the speed of the light, and deep into the relativistic limit, actually this relation got even changed or take the extreme form such that now energy and momentum is linearly proportional to each other. And if you really make this particle that's travel at the speed of the light, the only way you can do that is you have to make the mass of the particle goes to zero. So that's basically a curve that we expect that how the dynamic changes. From here to there, it's a really big changes as you really take the relativistic point of view. And that's kind of interesting new world that we are facing when you actually break this or send this particle up to the speed of the light. And there comes kind of our new windows opens up how to look at this high energy particle world. While the relativity is a very important one of the pillars, of course, in the picture, if you just go back, there are another important pillars that sets up. That's basically the quantum mechanics. And quantum mechanics comes from various different origins, but one thing that quickly demonstrates why we did quantum mechanics is clear that from this example I'm going to share. We know that all the atoms consist of the positive charged nucleus and the negative charged electrons. And of course, they have attractions because of these electromagnetic interactions, electrostatic interactions. Well, the way that electron doesn't fall into the proton and atom disappear is, of course, that the electron has some kicks of these energy, kinetic energies. So like this Earth is rotating around the sun, the electron is rotating around happily around the nucleus and can maintain some orbits that overcoming this attractive force between them. Now, this is a good picture, and this, in fact, was one of the first pictures one can set up for the simplest atomic model, except there is a problem. Unlike the Earth kind of rotating around the sun, for this case, the electron, when it's rotating around this nucleus, it is effectively accelerating. And Maxwell's equation tells us that if electrons start accelerating, there is some things happen. Basically, it should generate an electromagnetic wave or light, right? But then, if this light comes out, every time that the light comes out, electromagnetic comes out, basically lose energies. So it's a spiral down, and eventually should collapse down. And there is no atom should exist. But we know that we all exist made of the atom. So we actually effectively prove that something's wrong, and we have to fix this one. And this is what we call the classical catastrophe. Somehow we have to fix this one to understand this microscopic level of the physics in there. There comes that kind of many peoples here that showing that the founders of the quantum mechanics debated for about 10 or 20 years that how we can fix these kind of problems. And they come up with a very exciting and interesting and also intriguing concepts, such as that everything that we know should be in principle described, in fact, described by the wave functions, which actually relate with the probabilities and all these kind of things. But nutshell, this kind of all of the concept can be catalyzed into these equations, what Schrödinger wrote in 1926, called the Schrödinger equations, basically describe how this quantum wave or matter wave can be described in terms of wave functional form, right? Now, if you just kind of solve this wave equations, so Schrödinger equation, you get kind of interesting description of world, and that description can be quite different, in fact. For example, the hydrogen atom model I just showed you, the electrons circulating around this nucleus, if you solve these equations, had quite different descriptions, such as, now, yes, there's orbits, but this is not just kind of single, just well-defined orbits. Something like the cloud shape of the wave function distribution is what is a solution described by the electrons bound onto this proton. But moreover, most important part is those kind of orbits are certain numbers of it that is discretized. Orbit itself is continuously distributed wave functions, but energy associated with those kind of orbits are discrete. So there's only some discrete energy levels you can take out of these equations. And in some sense, the quantum world we describe is a world that everything is discretized. There's integer numbers that count the energy levels, count different type of the wave functions, and this discreteness is what actually determine or governing the microscopic world that quantum mechanics describe. So out of this one, many weird things actually comes around. So I will just show you one interesting experiments that describe that the discreteness that I was talking about. Let me start with some sort of classical description. I have some demo here. So this is, we found this kind of from this really downstairs basement, deep in there. This is old, the CRT, the cathode ray tube monitor. I think that young generation never seen this one maybe. Now, it's it's amazing that it's 15 years ago that this is something that everywhere, but now it's all gone, and everything's just kind of replaced by the LCD monitor where I cannot play this game. I remember that I played this type of things, and my parents almost kind of killed me because they thought I ruined their TV. So here's the magnet, and here's the old CRT monitor. I don't know whether you really play around these things before. You see that this, you see there that image is showing this camera. I'm just kind of bring the magnet, bring the close the CRT monitor. You start to see the distortions, right? Ooh, there is almost kind of gone through, yeah, right? This is okay for the black and white monitor, but if you just do it with the color monitor, you will see the discoloration for a few days, and you really think that you ruined this one. So you may ask that why actually these things happen? Well, magnet, of course, generate a magnetic field. And in fact, if you just open these things, which actually I don't recommend because there is high voltage, the electron guns backside, is shooting the electrons from the backside of this monitor to the screens, and when the electron hits, that will kind of brights up. And by controlling the electron guns steering around, you can see that these images. And when I just bring the magnets there, basically what you see here is electron start to deflect, and that's why actually you are seeing the distortion of the images, right? So why electron deflect under the magnetic field? Well, that's again going back to the Maxwell's equations. And we know that when the magnetic field is there, the electrons start kind of get the Lorentz force and it got deflected, right? There's a way that you can actually measure this more quantitative way than just doing that. So that is experiment was done some times ago, and in the following way. So now in this screen that you see that this kind of the cross, and the center of the cross here, basically there is a small piece of the semiconductor is there, right? And you see the cross that, let's see that, okay. So this side, we just apply the current. Okay. Along this one, we just kind of apply the current, and we can measure the voltage across this current directions. This is what we call the Hall measurement. And then you can imagine that if I just apply the magnetic field, right, and electrons start to deflect, and it turns out electrons tend to deflect the orthogonal to the magnetic field, right? And therefore, I should be able to detect the current between them. So that's basically measurement. So what I'm going to show you is indeed actually that's the case. So here is my voltmeter. I can turn on and measure the voltage. You don't see any voltage. Now I just turn on the switch. Now there is current start flowing through this small piece of semiconductor. And you can see that this poor piece, that N and S, there's a magnetic field going that way. So I will just kind of slowly insert this one into there. And I'm supposed to read the voltage got changes. And indeed, if I just move into there, my voltage got increases, right?
Wow.
And decreases, right? If I just change the directions, voltage actually goes the other way around. So it goes negative. It means that actually it's deflected around and the other way around. My screen, please. So you may say that, well, that's kind of simple experiments, right? Well, in fact, actually, this experiment was done. So this experiment was done 1879 by Professor Hall, and that was his PhD thesis subject back then, and that was a really big discoveries of what we call the Hall effect nowadays. Professor Hall actually, after PhD, moved to Harvard, and he became a professor here and served here about 40 years, including the department chairs, and it was a really important contribution, the scientific leadership here, including that further study of the Hall effect. Now, one can do this experiment much more the elaborate way than I just showed, but simply just kind of measuring the magnetic field and measuring the voltage across that tells you that how much electron got deflected. If you just do this in a much more controlled way, you will see something like this. Basically, this deflection, what you call the Hall resistance, is actually increasing with the magnetic field, which makes sense, right? Stronger magnetic field, there is more deflections. This actually plays a quite important role, especially the slope tells you that how many electrons into this solid can be described by this kind of slope. And this has been one of the important techniques widely used in semiconductor industries to know that if you want to know that how many electrons in your sample, in your semiconductor, this is a measurement you want to do, right? Now, however, this is all classical description, nothing quantum yet, right? But we can make this kind of quantum description. It comes around, the quantum description of this experiment come around another probably almost 100 years later, done by in Germany by Klaus von Kliching. What he wanted to do was quantum mechanical version of these experiments. To enhance the quantum mechanical effect, one need to do some things, such that you want to actually put down electron in much more confined space, so-called the low dimensions. The way that he achieved that is starting with the silicon, piece of the silicon, and put down the electrode on the top, but not touching the silicon, apply the voltages that will induce the charges underneath of this, the so-called gate electrode, accumulate at the surface of the silicon. And using that very thin layer of the electron sheets, he measured the Hall measurement. And he did use extremely strong magnetic field, several Tesla, which is probably about 10 times larger than the magnetic field I used there, and did very low temperature. First actually did at the higher temperature, and then kind of usual Hall effect, and slope will tell you about how many electrons in this system. But what is interesting things happen when you actually cool down the sample to the low enough temperature, where quantum mechanics kind of plays an important role in solid system. And he discovered it doesn't change continuously, but there's step appears. And this discovery done in the 1980s is what we call the quantum Hall effect. And you see why they call it quantum, because it is not continuous. Some discreteness actually comes in. In fact, this discreteness is closely related to what I mentioned before. One can first find out that some regularity in this discreteness, and not arbitrary steps. If I just call this is my first step, turns out the next one is half of the first step, height, and third one is 1/3, and fourth, 1/5, and you can see that this one actually has regularities, integer numbers associated with each of this plateau appears in data. why the plateau appears? It turns out this plateau is closely related to how the electron wave function should look like. Electron wave function under the magnetic field, since the electron is orbiting around, has some interesting kind of properties, what you call the winding number. In other words, if the electron really make the circle, right, how many circles you make before it just comes back? That's basically what you call the winding number, the electron's wave function under the magnetic field. If it is just wind once, 1, 2, 3, 4, and you see that why the step is appearing in the integer, simply because it is related with those kind of discreteness, the quantumness I just mentioned. So that's basically the essential part of the understanding the quantum effect. This effect, in fact, appears that if the condition meets the relatively large sample. So it is macroscopic, one of the macroscopic quantum mechanical effects you can see. Well, maybe this one is not kind of weird enough. So let me just kind of see that everybody expects something weird in quantum mechanics. So let me just kind of give you one example that I found is really, really weird, but also it's extremely important to explain some of the physics that I'm going to discuss. That's about the spin. Now, story about the spin comes from the, say, electron. We all know about the electrons. We just described about the electron. Electron is charged object. So like this charged object, if you start kind of spin around charged object, you can effectively think about the current loop there. So there is a magnetic moment sets up. Now, if you just have the ball, the charged object is spinning around, that magnetic moment can direct any directions in the three-dimensional space, right? So I can just kind of bring any directions of this magnetic moment. Simple question for you. How many axes, how many coordinates I need to describe this direction of this magnetic moments? 1/5? Oh, I don't know. I would say that this is a vector in the three-dimensional space, so I need 3 coordinates to explain that, right? Up, left, or the back. That's basically the 3 coordinates I want kind of describe this one. But what happens is, if you just kind of make this quantum mechanical description, turns out that's not the case, especially electron spin, what you call the spin half object. I need only 2 axes to describe that direction of this spin. Only up and down direction is enough to describe all this direction of the electron spins, which means even if electron is kind of pointing in that direction, somehow, if I just use electron spin wave function up and down, I should be able to describe that. That's basically weirdness. It doesn't look kind of esoteric and doesn't sound too weird, but there's an important conclusion you can make out of this so-called 2-componentness of the electron spin. This is that description. Out of this description, we have the following conclusions, such that if I have the electron wave function, what if that I turn around the electron 360 degrees, and what happens? If I'm turning around myself 360 degrees, you see that myself didn't change, right? But that's not the case for the electron. Electron wave function, spin wave function, if you turn around 360 degrees, it comes back almost itself, but sign changes. -1 in front of you, right? That sounds quite bad, right? But then I can make it kind of better or make it itself if I just turn twice, right? Once you get the negative sign, another time you get another negative sign, that negate the negative sign, I get the one myself, right? So that's actually a weird case because somehow I'm telling that for the electron, unlike me, that you have to turn twice to come back itself, right? What kind of weird object it is? In a sense, this is one of the quantum weirdness we can find easily to many of the particles, including electrons. There's a very interesting object I can just bring you that carries very similar things. That's Mobius strip, right? Anybody probably didn't make the Mobius strip in your life? You can just do that in home. You have the strips, not making loop, but twist it, making loop. Then you get this Mobius strip. It has a weird property, such as you can just try out. Starting from one side, pointing out that directions, and try to turn around 360 degrees. Then you will see that you are not on the same spot on the opposite side, where the direction of this spin that you start to turning around is exactly the opposite. If you make another turn, then you come back, right? So that's somehow interesting analogies I can make that how weird this structure is, right? Now, this actually describes about one of the quantum weirdness, right? But story actually goes on beyond that. Spin that I just mentioned is a very interesting object in some sense actually couple between the relativistic physics I was describing versus quantum physics. I told you that two modern pillars of the physics, the two pillars of the modern physics is relativity and quantum mechanics, heralded by the Einstein and Schrödinger equations I just wrote here, right? Spin, in some sense, actually comes in as additions of this orbital, the description of the wave functions, as just kind of its own degree of freedom, so I can just add up. Then you can ask the following questions. Are these two theories compatible with each other? If you just look at that, in fact, they are not compatible with each other. It's already clear when Schrödinger wrote these equations. This is not relativistic equations. Doesn't hold in the relativistic limits. So what would you do if you go back to that time? Well, that important problem is we have to fix this one to make the relativistic compatible to quantum mechanics. It's amazing that it only takes 2 years that actually relativistic quantum mechanics actually comes out. It was Paul Dirac's work, one of the figures in that original figures, worked it out within 2 years and make it completely compatible, that relativistic quantum mechanical equations, now we call the Dirac equations. There are a lot of exciting things about the Dirac equations, but one thing really exciting is if you just kind of describe a completely relativistic particle, such as particle without mass, that this Dirac equation solution describes quite weird things. First of all, now you see that this linear dispersion relation, energy and momentum that I told you in the classical the relativistic dynamics, that actually appears, except that there's additions, there's counterpart in the negative energies, where in fact you can create these so-called antiparticles over the particle. So that's already a weird concept. But another important part is, turns out in this theory, the spin is completely incorporated into the your descriptions. Unlike the Schrödinger equation, you just kind of add up as additional degree of freedom. Here the spin is, especially in the relativistic limit, exactly locked into the momentum, such that spin is either parallel or anti-parallel with its momentum case. So this is what we call the chirality. And those kind of concept naturally appears when you take this completely the relativistic equations and brings up that now a theory that both compatible with the relativistic physics as well as quantum mechanical physics. Now, this is about the mid lecture, about 30 minutes past. So I think this is a good time that I can give you a quiz. Right? So I'm prepared, right? So there's a relativities. I just talk about the quantum physics and there's a relativistic. Quantum physics, I will start high then quiz. Yeah, no, I will not do that. Yeah, because now this is basically I would say that few years of, well, actually, especially on this relativistic quantum physics part, this is only the subject that when you get into the senior level of the college, you start kind of learn about these things. Maybe even just the graduate level of the quantum physics start to discuss about that. So I know that this is too much. I just compress everything within 30 minutes. I'm not sure how I succeeded. Doesn't matter. You don't have to remember everything here. But I want to actually remember the 3-4 figures that I'm just showing you now that basically summarize what I'm just telling you here, right? First of all, in the relativistic limit, I expect linear dispersion relation. In other words, energy is proportional to the momentum. That's one of the important part. And completely relativistic particle, there is no mass, right? And second part is quantum mechanics tells us that discreteness is important, and especially quantum spin that turn twice to go back to itself, right? So that's kind of another important part. And finally, if you just combine the relativity with quantum mechanics, in the relativistic limit, you expect the so-called chiral particle such that spin direction is tied with its momentum direction. I can tell you that one good example that match all of these things I'm just talking about. To do those kind of experiments, you have to go here. I think something is kind of cutting off, but actually you get the most of sense. This is the CERN, LHC, Large Hadron Collider. Melissa usually often go there to do experiments. And this is a kind of good experimental approach. We can test it out, that theory, relativistic quantum mechanics, because we need to accelerate this particle up to the close to the speed of the light, right? Now, this one is using as an accelerating hadron, large hadron. such as gold or lead type of the atoms. But before it was used as electrons and positron acceleration. So imagine that I have an electron, spin half particles, fermions, right? And there's the spins. And then I start to accelerate the particles, right? And what you see here is that this is what you expect to see if we just kind of see the electrons in this size, right? Electron is circulating around. Its momentum is along the circumference length. I mentioned that if it is accelerated up to the speed of the light or close to the speed of the light, it becomes chiral, means its spin direction is either parallel or anti-parallel with the momentum, right? And the other thing you have to remember is to be the electrons comes back its own in terms of wave function, it should rotate twice rather than once. Because if you rotate one, your wave function gets the minus sign in front of it, right? So these are kind of really beautiful experiments, a beautiful concept. But as I mentioned before, this one only comes and when you start to appreciate, only when you learn the advanced quantum mechanics in the relativity limits. People like me who worked on the condensed matter physics, or Melissa say chemistry, basically this is usually not the topic that I usually familiar with, right? Because, well, we are dealing with the materials and a lot of atoms here, a lot of electrons there, but nothing's moved up to the speed of the light. I think they are usually at the best about 1% of the speed of the light at the best. So relativity is not too important. I mean, the quantum mechanics is important because I need to describe the electrons in such a small length scale. But relativity is, well, you learn in the undergraduate. But for the research, it was never hit me actually important topic until probably about 10 years ago. And that's basically the story how it goes. So people like me that who work on the materials and their properties got interested in that, looking at all these atoms and electrons moving around. There are many, many atoms. This periodic table, if you look at it, there are many, many atoms. There are many combinations. There are zillions of the millions of the materials that you can study about. Today, I'm going to describe only one element, and that's already enough. That the quite exciting story. The element I want to kind of tell you about is carbon, number 6 atom in this periodic table. There are 6 electrons, but among the 6 electrons, 2 electrons is deeply locked into so-called the core orbits, so they don't do anything in terms of chemistry. And 4 electrons actually do the quite interesting chemistry, or condensed matter physics. So here's the example. So this is the example of the materials, atomic materials made of the carbon. So you can see that this vortex is made of the carbon, right? And I told you that there are 4 electrons make this chemical bond. So there, if you count these arms coming out, there's 4 arms coming out, make the tie. And this is only made of these carbons with all these 4 electrons that participate in chemical bonding. Anybody know that? What is this material? Yes, good. So this actually forms the diamond, right? And if I just replace this carbon into the silicon, which is one law below, that's basically also the atomic lattice structure of the silicon, and so on, right? So there are many things can be explained here, but this is not my topic. My topic is yet another interesting structures that this carbon can make, something like this. Now, this is a different case, right? Basically, what you're seeing here is hexagonal shapes, or the honeycomb shape, right? Then, if the vortex is carbon, how many arms you can see there? 3 arms, right? Well, where is the other electron goes? Well, the other electron actually is still there. Turns out that's what chemists call the sp2 carbon bond, where the 3 electrons make this strong bond nearby, what chemists call the sigma bond, which form the backbone. But then each side, there's 1 electron remains, right? What this electron will do is that can be shared with all other carbon atoms, right? In fact, there's molecules that actually do these things. This is basically benzene atoms, right? Whenever you see the benzene atoms, there are 3 arms that are connected with the nearby, but there is 1 electron per carbon atoms there. What they will do is they will be shared with other carbon atoms. So in a sense, this is the molecular wires that electron can just kind of circulating around. You can see that you can connect these benzene atoms and make a lot of different molecules, what you call the organic molecules. Some substances made of us. Benzene rings, whenever you see the benzene rings, you can see benzene ring. For the physicists, so we can see that there is an electrons network that's sloshing around this type of this network. nature, in fact, allows us to do these games even larger scale. Over the past 20 years, or actually including the graphite, which was first seen by just stacking this type of materials, right? Discovered probably about several hundred years ago. Through that quite recent kind of discovery, such as buckyballs or nanotubes, or now even graphene, that nature provides us materials that consist of this so-called sp2 carbon bond, network of carbon atoms, electrons can sloshing around, so many different cases, and even spans the different dimensions. It's kind of intriguing and interesting that discovery of this system comes around kind of different way. Of course, graphite has been known for a long time, and then fluorine was discovered around 1985, and the nanotube was discovered about 1990, and graphene comes around about 10 years ago, and that spans kind of interesting period of the time that where people start to realize that there's interesting this carbon-made system do exist in kind of different dimensionality even. Among this system, in fact, the graphene, the single atomic layer of this graphite is, in a sense, most important quantity because that's basically the basis to form the all other system. If you start with the graphene, stack the graphene together, you can make the graphite. If you just roll these graphene sheets, you can make the nanotube. If you just carve this graphene down and fold it up like this, it becomes fluorine, right? So everything's in some sense, if you understand the graphene, you can understand others. In fact, that's a case that historically, the quantum mechanical descriptions to drive that how the electron moves in the graphene lattice, basically turns out that there's two components comes in, because each of the graphene lattice comes up the different configuration of this atomic lattice. All this description was made actually in 1947 by Canadian physicist Philip Wallace. What he found was quite intriguing though. Because of those symmetry that I just described in previous slide, there are two components of the atoms in the graphene. Make this graphene description, electron moving into graphene lattice, almost look like the relativistic. What I mean by is, if you look at this energy versus momentum relation of the electron in the graphene, can be described, especially in special case, with this linear dispersion relation I was talking about before, for the effective Dirac equations, right? Where the chirality comes in, coming from these two components of the graphene lattice. So already back then, many, many years ago, 50 years ago, 60 years ago, physicists start to think about, well, if you have the graphene lattice, it can be quite exciting and interesting to study, because there is some interesting analogy can be made with this relativist quantum mechanics to beat these high-energy physicists. But it was quite difficult, because how you can actually get this one single layer graphene out of something, or how you can make it. So the story goes about 12 years ago that when I studied as an assistant professor in the Columbia University, and then I was thinking about, well, one of the interesting topic maybe I can just explore is let's try to understand the electronic property of graphene. And the first question comes around is how you can prepare the graphene sample, right? But then I thought kind of the other day with my friend, my first student, Yambo Zhang, think about how you get the graphite easily. You can break your cell phones open and then your battery contains some graphite lead, but that's kind of catastrophic. But then the next thing is you can just get this pencil. And we know the pencil lead is made of the graphite. If you just zoom in the pencil lead, in fact, you can see that a lot of stacks of the graphite is there. So if I just bring this pencil right into the paper, you will see that this mark, black mark, if you just zoom in, maybe you can find some thin layer of the graphite in there, maybe even graphene. So maybe this is kind of one way you can do that. Except that, of course, pencil is a macroscopic object, and I'm talking about one single layer of the graphene atoms, how you can do these things easily. Well, that's not easy. So here comes my first student, Yambo Zhang, actually came up with the ingenious idea. Well, why not we make the pencil small? Let's make the nano pencil, right? So that was the idea. So how we can do that? Well, we started from the graphite, chunk of the graphite. He made the very tiny, tiny blocks of the graphite blocks, about the micron size, carve it out from this bulk graphite. And then there comes so-called the atomic force microscope, which actually has a very tiny cantilevers, and then attach this block, carefully take that out from here and attach onto the block. And there comes nanopencil, and then you just kind of bring it down to the substrate and clip it off, and hoping that you can get very, very thin layer of this, the graphene or graphite blocks out, such that we can study that. I would say this is a wild idea, but the Yambo was really ingenious, and he actually succeeded to make the dispenser as you see here. Now, I should kind of tell you that really appreciate that how difficult it is in the following way. Anybody know that what it is? Yeah, this is famous that photographs you can find in Google, right? This is human hair that magnified using this scanning electron microscope, right? Usually depends on the person, the size of the human hair is about 100 nanometer, 100 micron. So that's the length scale that we are talking about, right? The pencil we made, compared with this, is about this size, right? So how to make this one? We need kind of quite a bit of efforts and a special tool to do that. But nevertheless, once we make this one, we just kind of cleave that off this thin crystallite onto the silicon wafer, and indeed it worked, and we got kind of quite thin crystallites here, and we wired up, and we just measured their properties by sending the current and voltage, more elaborate measurement than we did here, but we did that under the magnetic field, and we got a beautiful result. And we are really proud of that, because this result, we actually got up to this about 5 layers or 10 layers of the graphene. So it was not a single layer, but we are very close, right? We starting from this bulk crystal, clip it down to, say, 5 layers of atoms. I think we are almost there, right? Many of those magnitudes went down just kind of another factor of 5 that will get to the single layer. And already the result is great. So we just kind of write the paper, submit the paper, and just waiting for the response back from our referees. About the time that we heard a kind of interesting rumor saying that we are not the only one doing these crazy things. And then a few days later that we heard about the rumor, that I start to see that the paper was circulating, and then we found that we are completely scooped by these 2 guys that work in the Manchester University, Kostya Novoselov and Andrei Gain. And this paper was published that few months after that we just submit our paper. And when this paper, that I remember that the first day that I was reading through this paper, I had 2 shocks. The first one was, of course, that the feeling of the completely scooped. Well, it's a real complete scoop, because what they claim here is that they went down to the 5 layers, but not only stop at the 5 layer, they demonstrate they can get down to the 1 single atomic layer, right? And then they got the very beautiful data, even better data than we had, right? So our data is basically a subset of their data, right? So it's completely scooped, no excuse. But then, after 2 years of the hard work, then what do you expect to see is, well, so we want to find out how we got scooped. And we made this beautiful, elegant nanopencil. Well, what they did actually, what they do these things. Turns out, if you read this paper, they use Scotch tape to get these crystals. And it was literally Scotch taped. I brought some demos, actually, try to even demonstrate. Here's my Scotch tape. Here's my graphite in the box. And I have the wafer, but I think that I don't have enough time to go through that demo, so I'm not going to do this demo. And another real shock comes a few years later after they got the Nobel Prize, by the way. But it was actually quite kind of amazing things. And then I can even just kind of show the demonstration. Anybody interested in, after this lecture, I can show you how to do that. But really kind of using the Scotch tape, crush the graphite crystals and scrubbed onto this silicon wafer, you get the graphene out there. Of course, you get not only graphene, but also the junk. But the important point is, if you just look at very carefully, among this debris of the junk that you get onto the silicon wafer, you can find a few layers down to even single monoatomic layer of the graphene out of it. So that was quite an amazing story, right? Although that's kind of such a rudimentary technique, you can actually access a single atomic layer. And of course, we learned these things, and we got really depressed by such a simplicity. Next day, that we just kind of run through the stationary store, bought the Scotch tape, and Yambo just kind of do this experiment. Within a week, actually, we reproduce what they are getting. So amazing stories that we actually learned. And that happens only 10 years ago. That's exactly 10 years ago. So although this is a really kind of, you can say, dirty kitchen physics, or dirty kitchen even science, right? You don't want to even call the physics, right? Well, the next level is more complicated. I think that, of course, you have to wire up. This is a relatively small object. You have to use this modern technologies to do that. And if you just go to the next building, what you call the CNS, there is the facilities that how you can make the small computer chips out of it. Basically, that's the technology that we need. I just brought in one of the devices that we first made. This is the device. You can hardly see that. Maybe you can just bring it here, whether I can just show you. So this almost looks like computer chips, right? So in the central part, basically there's silicon wafers, right? And then onto the central part of the silicon wafer, there's a device with a graphene. We actually connect these thin wires down to connect to that one. So it's a very, very tiny length scale that we can make the device, right? So what you can do is you just kind of make this so-called device or graphene transistor. We just kind of stick into the, now we can go back. We can stick into the cryostats and measure the electronic properties, or basically how the resistance changes. You can start to see all sorts of interesting things related with this linear dispersion relations and relativistic physics I was talking about. I will show you the one important example that basically linked all the things I mentioned so far, right? I told you the graphene lattice has this hexagonal lattice, but because of this interesting symmetry, that there are two different kind of the categorized carbon atoms, although they are the same carbon atoms, depends on the chemical link they make. They is connected to so-called inversion symmetry. They have this interesting link, right? I told you there's a linear dispersion relation for electron dynamics that working in this lattice because of this. And there is the spin-like object, or more precisely what you call the pseudospin, but coming from this two-componentness that has a spin half. And should be chiral, means that when you apply the magnetic field, electrons start to spin around in this lattice. That's kind of amazing things start to happen, right? When apply the magnetic field, the electron spins around. Electrons start kind of dragging its spins around, or more precisely pseudospin, but that pseudospin start to turns around together with the electrons, right? Because of magnetic field, right? But then you should remember that when electron turns around in this graphene, it should turn around twice to go back itself. If you turn once, it's only effectively half turn you are making. Graphene is extreme limits of the two-dimensional system, in a sense that the thinnest material we can get. So what you expect here is basically when you apply the magnetic field, go down to low enough temperature, you will see the quantum Hall effect. Indeed, you do see the quantum Hall effect. But because of this, your quantum Hall effect can be somewhat different, right? Before, we got the one step, half step, or the 1, 2, 3, 4 associated with this kind of winding number, right? How many turns you have to make to connect that. But what is being changed here? If you make this one turn in orbit and make the one complete set, before we call this is winding number 1, because it's winding once. But what is winding number I have to assign? It becomes only half. I have to turn twice, but I have only rotated once. So it becomes half. Now this becomes 1, and now this becomes 3 halves, 2, 5 halves. What you expect to see here is the step appears not an integer number, but half integer number. So that's really important difference. And this can be testable experimentally because step is appearing in your measurement. Indeed, only 1 year after the first discovery, both of group, now this time we didn't get scooped, luckily, start to see that indeed that's the case. When you measure the quantum Hall effect in graphene, they beautifully shows up and the step appears half integer rather than integer. Really showing that electron dynamics in graphene follow through that the relativist, what is relativistic quantum mechanics predict. There are more stories actually related to this one. For example, that if you look at the quantum tunneling problem, which is a very exciting problem itself, in a sense, the quantum tunneling problem tells you that when you have the barrier, classically all the ball that if I throw on the barrier will back, but in quantum mechanics, because the wave functions can leak into the barrier a little bit, there's a finite, but there's small might be, but finite probabilities that it can tunnel through. So in other words, if I just bang my cell phone into this wall, probably for me, the macroscopic object, I have to do many, many billions of years to kind of quantum tunnel through. But at some point, it may actually happen in this, right? For the electron, small object, this is readily happen. Now, the same thing if I just apply the Dirac equation, so-called the quantum electrodynamic description, actually tells you even weird things, such as, well, for the quantum electrodynamics or the relativistic quantum mechanics, if you just do experiment, it'll always tunnel through. Basically, that's the description. And it's quite paradoxical, and often people call this is basically Klein's paradox. How can it happen? In fact, actually, this actually happens quite readily. Any quantum mechanical particle, such as, for example, the photon, completely quantum mechanical particles. If you go out in the rainy days, see that the thin membranes on the water, you will see this beautiful color appears. And this is the reason that what you call the Fabry-Pérot oscillation, but nothing but just the interference of the photon across this thin layer, describing the waviness of the photon. And in fact, if you just use this property quite well, you can make the so-called this anti-reflection coating such that any electrons or any photon comes in, always tend to go through rather than reflect it. If you just choose the right thickness of the membrane that relative to this incoming wavelengths of the photon. Now, in principle, you can do this experiment for the electron, especially relativistic electrons. If you use a graphene lattice, graphene device connected with all this wire, and make this thin gates on the top to create some of the barrier in between, basically you mimic that experiment done into the photon for the electron case. And indeed, if you just do that, you will see the beautiful patterns appears, like the Fabry-Pérot oscillations, and more importantly, this oscillation period can be modulated by the magnetic field, because I can steer around the electrons in that way. What is exciting thing is, if you just look at this modulation of this periodic oscillation, then you will see that there is indeed these two components of spin. In other words, chiral electron property can be read out, these oscillations. And this type of experiment was very difficult to be done in typical case, because you need not only the high energy particle, but the barrier stiff enough to realize that. For in the graphene, you can do that into the device form on the table top. So that's quite exciting things. But the real point of the graphene research, in some sense, is not only the science, which is exciting. In fact, it is the application point of view, which can be quite exciting. I already told you that graphene, it's indeed kind of cut it off. There's now mobilities in this axis. Electron move fast in the graphene because it is described by this relativistic descriptions. So you can imagine that the electron moves really, really fast. Turns out, if you measure, this is more or less velocity of the electron as a function of how much electrons you have. Turns out the mobility of the electron is way, way higher than mobility of electrons in any conventional semiconductor, not to mention of metal. Which means that if you make the transistor or device out of graphene, it works really, really fast. Recently, that has been demonstrated in the IBM groups. They make the graphene transistor on the wafer scale and demonstrate this transistor will operate really fast when it's made of the graphene. So there is some of the interesting application might be possible. Graphene is also optically very interesting. Although this is a single atomic sheets, there are a lot of electrons can absorb the light, and it is a good conductor, as I mentioned. You expect the light may not go through well. Turns out most of the light goes through, about 98%. Here's the example that done in the Manchester group. They actually suspend the graphene into the hole. Here's a one monolayer, two layer of the graphene. This is just kind of through hole through the air. Then you see that it's slightly darker and more darker here, showing that even if it is a single atomic layer, it absorbs small amount of the light, about 2%, and most of the light goes through. So it has a kind of interesting optical property. More exciting thing is if you have the same sample, now this was done my colleague at Columbia University, Jim Horn's group. What they do is those kind of the suspended graphene, they just try to poke the hole through using the AFM tip. And often they found that their AFMT made of silicon is broken off. And only when they use a diamond tip, they can make the puncture through the graphene layer. And if you carefully measure how much force and how much deflections you induce onto this graphene, suspended graphene, they make the conclusions that this graphene can be extended up to 25% without any damage onto the graphene sheets. And if you measure the strength of that so-called Young's modulus is extremely, extremely strong. So if you make the analogy, if you have this is a sheet of the graphene, and you can actually put the elephants, they're balancing onto this pencil tip, entire elephant weight is balancing on the tip, and press the graphene, and still it can withstand all those kind of stress and strains that supplied by this heavy massive object. So you can see that this is effectively really mechanically good materials. Combining all of these properties, such as the good electronic property, good optical properties, good mechanical properties, even good chemical properties, there are now a lot of applications people are thinking about. There are some things that are very high-end, such as replacing some of this silicon technology, which is extremely hard. I'm not sure whether it's realizable. But one application might be close to the reality is the following things. I just kind of brought this the demo that my colleague, Professor Byung-Hyung from Seoul National University, actually happy to lend us this demo. One interesting application you can think about is using good conductions, high mechanical properties, and good optical the transparency is using this as a flexible screens, right? So all the kind of smartphone we have, there is a touch screens, which requires good mechanical flexible enough, but yet there is a kind of good transparency and good conduction is needed. There might be graphene is a really good candidate, and people are really serious thinking about that. You may say that, well, if you just make this kind of touch screen out of scotch taping out from the graphite, how many years we need to make these touch screens? Well, over the 10 years of the last time period, people actually have developed a many different way of producing the graphene. Now, here is one way that produce graphene using the so-called chemical vapor depositions. In these plastic sheets, there is a graphene sheet is coated here. So now you can see my face through the graphene, right? Can you see me, right? 98% of the light is actually transparenting. So it's very difficult to see that. Only when I just kind of put these things, you can barely see that. I think it's very difficult to see. Anybody interested to see, just come down and take the look. You can see that real graphenes there. They can make even larger sheet than this one now. Can be produced in terms of meter scale by this kind of industrial method. Not only doing that, you can see that this one is already patterned, the graphene, into the almost, you can see the size of the iPhone size screens. They are really started making this into the really touch screen form to be used. Whether this will be at some point in our phone or not, I don't know, because it's always kind of competing technologies and all other things. But already pilot programs or prototype device was formed by the graphene into the kind of reality. So that's kind of one of the examples that sometimes this exciting fundamental science, only 10 years old, actually has some implication for the even application. All right, so but that's actually a starting point in some sense. Graphene is the first material we see that we can extract from bulk or synthesize bulk down to the one single monoatomic form. But turns out nature provides us many of this type of the materials. There's boron nitride, there's a transition dichalcogenide, some of the high temperature superconductors, organic and inorganic materials. Many of these materials, actually, you can cleave it off or you can synthesize down to one monoatomic layer. Not only that, they actually shows various different properties. Some of them become semiconductor, metal, or some of them becomes even superconductors. And luckily enough, because interlayer, there's not much interactions, so you can actually restack them. So build up again three-dimensional structures out of these functional properties. All of these exciting things, in a sense, initiate from the graphene only 10 years old field. So that's kind of one of the exciting fields that we actually lived in. Those relatively new materials start kind of produce exciting science, as well as exciting the opportunity of the application, as well as the new directions of the material science. So I will just conclude with this slide. this slide shows that what kind of combination can be made. I made a couple of jokes to the Melissa. I always try to provoke my high energy colleagues. But in my personal experience, the past 10 years was extremely interesting 10 years, because that we see that this new materials forms and new materials start having a new field. But not only that, that's a field that somehow I start to see that the old memory that I learned about the Dirac equations in some of the advanced quantum mechanics graduate school, and I completely forgot about things, becomes not only just my test, but it comes back in my lab, becomes extremely important to understand something happens. And this is a good example that why this synthetic idea is important. Sometimes it's completely unrelated things, but happily combined together. And this is only the first example I'm seeing. I want to see more of this example between, say, chemistry to the physics to the biology, and all different fields. Maybe more and more synthetic idea may comes around. With that, I'd like to thank your attention. And last slide is my group for all these things make it possible.
That was amazing. I actually understand it now. I think public lecture is the greatest level for me. Are there any questions that people want to ask? Do we have, our main person is normally, I'll be the person. Sorry.
Thank you. Thank you for the great lecture. What is actually the largest piece of graphene that you can produce today in the lab?
Okay, so with the Scotch tape method, somehow it's still produce the best sample we can get. The large sample is about 100 micron size, so it's about your hair thickness. However, the chemical vapor deposition I mentioned here is producing about the meter size of sample with continuous roll. So I think that there is no size limit to produce graphene in some sense. Although that they tend to be not the highest quality, but at least it's a single layer of the graphene.
Thank you.
So when you did that, when you said that electrons have this weird property where you turn around a whole time and you get a minus sign. Well, when you turn around, you're made of electrons, right? So does that mean that you gain minus signs every day when you're turning around, or can you detect that?
That's a very good question. It's an interesting question. I never thought about that. So I was wrong maybe when I just showed the demonstrate. It looks like they equal, but you're saying that, oh, you have the minus signs in front of you, right? Well, I think that this is related with the so-called quantum coherency. Because to get these wave functions, the minus signs and so on, to make this is meaningful. Indeed, if you cool me down to the absolute zero temperature, I'm sure that if I turn around, I'm not leave the back then by that temperature, that your wave function got the negative sign, right? However, in the macroscopic object like me and the live in the room temperature, it's very difficult to make this quantum coherency. The negative sign in front of wave function means it has phase shift of the wave function correspond to the pi. And that phase is rather delicate and easily destroyable. So in the macroscopic object, so it's probably not me with the negative sign is me. You're doing some exercise today.
When you say the energy is proportional to the momentum,
yeah.
What is the proportionality constant there?
What is a proportion? Why there is proportionality?
Yeah, but what is the velocity?
Oh, I see. Okay, so that's a very good question. In the really, so when the electron, the momentum is proportional to the energies, the proportionality in the relativistic physics is the speed of the light. Now in the graphene, it is not real real relativistic quantum mechanics. It's like the analogy, I would say. Analogy comes from that basically, if you solve the Schrödinger equations for the graphene lattice, that's where this analogy comes around. Turns out that proportionality is what we call the Fermi velocity of the graphene. Actual number is about 100 times smaller than real speed of the light. So it is not true that the relativist quantum mechanics, it is pseudo the relativist quantum mechanics, meaning that mathematical structure is the same, but real number-wise is different. So that's why I think many of the relativistic experiments can be done on the tabletop with the graphene, because it's pseudo-relativistic.
Okay.
Correct, yes, it still satisfies the Dirac equation. So mathematical structure is there.
So let's thank the speaker again, and then you can come down and ask questions. So thank you very much.
Thank you. Thank you.